Brandon Friske from Quinn Evans Architecture in Ann Arbor, Michigan. He's speaking on evolution and project workflow this morning. Brandon's an architectural designer in the Ann Arbor office at Quinn Evans, and he received his Master of Architecture from Lawrence Technological University in 2010. He's currently a member of APT, Eastern Great Lakes Chapter. He's been a featured speaker for laser scanning and technology at the Iron and Steel Preservation Conference and the Michigan Historic Preservation Network Conference, as well as various regional venues. We welcome Brandon this morning. Thank you.
All right, thank you. So I work out of Quinn Evans Ann Arbor office in Michigan. Along with our Ann Arbor office, we have a sister office in Washington, D.C., and two smaller offices, a new one located in Detroit, Michigan that we just opened, and another in Madison, Wisconsin, that we operate our landscape architecture out of. Our company specializes in historic preservation and adaptive reuse projects with the goal of preserving our cultural heritage and our built to natural environments. And our focus on historic preservation and adaptive reuse projects provides us with the opportunity to work on many different project types, using many different approaches and different technologies. And today my presentation is going to look at the history and the integration of high definition survey into our evolving project workflow, as it is one of the key technologies that assist us now across multiple project types. But before I jump into examining the impact and importance of high definition survey to our workflow or our process, I'd like to look at how that core workflow has evolved over time. And it's only approximately 30 or 40 years ago that architects and engineers were documenting projects almost exclusively by hand, with the most simple goal of getting the intent of the project on paper so a contractor could build it. And because it took so much longer to document by hand, the number of sheets and the information represented on those sheets was more valuable, much more valuable than it was today. And that's how you end up with drawings like this, the one pictured on your left, where it's almost like a piece of art rather than a construction document. And then somewhat reluctantly, computer-aided design, or CAD, moved in to replace hand drafting, leveraging the computer to organize, produce, and alter project documents at a much faster rate. And had the same overall goal and the same process, except it became much more efficient and machine-like, and you lost that sort of artistic quality that you got in the older drawings. And the most recent change to the industry came with the addition or introduction of BIM, or Building Information Modeling. And unlike CAD, BIM truly changes the way the industry works, where we no longer draft in the traditional sense, but actually design and build true three-dimensional virtual representations of physical objects. And these can embed information, they can be tracked and measured and changed globally. So if you make a change in one view in your document set, it'll update throughout the entire project, and that's because you're affecting a single model and not separate isolated images like you normally would in CAD. And then that model can be manipulated and dissected to show the information needed to document construction. Sorry. And then BIM also supports a more collaborative project, allowing multiple users and industries to work within a single environment. And this ability reduces the chance for mistakes during construction, as problems and clashes can be discovered and worked out in the model before construction ever begins. Or at least that's the goal most of the time. And we are definitely still learning to adapt to this technology, and this image clearly shows that. Many times you have a lot of hands in the model and things aren't always coordinated well. That's because BIM requires much more input and advanced training and knowledge to use it. It also requires much more communication between the model users. So consequently, there's a much greater chance for error. However, the flexibility, visualization, and collaborative benefits can greatly outweigh these disadvantages by saving money during construction and ensuring that the design is thoroughly tested and worked out prior to implementation. And since the real money for most projects is spent during construction, this is a pretty small price for us to pay. So while CAD contributed to the evolving project workflow as far as increasing the speed of documenting a project, BIM has given the industry a way to better plan, analyze, understand, and design a project, using technology more efficiently and not just as a computerized pencil, which is what CAD sort of started out as. And that quickly brings us to where we are today. And you can see that like most things which involve or employ technology, our core process is advancing at an exponential rate. And along with this advancement comes a rush of supporting technology to dissect and analyze a project. And this is especially important for preservation and reuse projects where an extra layer of knowledge and information is required at the planning and design phase. Many times when we intervene with modern technology and systems, it can have a devastating effect on mature buildings or structures. So before a proper solution can be provided, investigation and analysis are needed. As architects and preservationists, we have a duty to ensure that these resources continue to provide for their users and survive their new interpretations and uses to the best of our abilities using all the new tools we have available to us. And up on the screen is a spread of various programs and technologies we use in our office to help us during the design process. We perform energy studies, we do material testing, structural investigations, and hygrothermal analysis, which is the monitoring of moisture through a wall assembly, for instance, if we're adding insulation or changing an existing construction, to make sure that any of the changes we're making do not have a negative impact on the structure. And all this can be done on the fly as part of our design process, giving us insights into our decisions for the reinventing and preserving of our valuable resources. And these abilities help evolve engineering architecture by lessening our reliance on time-tested methods and designs alone, and offering a higher level of prediction for our design outcome. And while these new abilities are amazing and promise new levels of detail and understanding, they also require extensive knowledge to use. So beyond staying relevant, this knowledge is needed to truly take advantage of what our new technology can offer. So moving forward, industry professionals are going to have to either constantly educate themselves just to understand their projects, or specialize themselves to better communicate or better contribute to the overall process. And our job right now is to filter through and streamline this evolving process and make it efficient, and find out what we can take on as part of our own workflow within our own office. And one piece of supporting technology that has become almost invaluable for us, and something we've decided to take on ourselves, is using laser scanning and point clouds. And I've presented in the past on the use of point clouds and laser scanning, focusing more on how we as an architecture firm employ it to extract physical information about a structure or a resource, viewing it basically as a highly efficient supplemental survey tool. But as we've become more experienced with using scanning technology, through a close relationship with our local scanning and civil engineering office, and also through our own exploration of the technology, we have found many more uses for it beyond recording existing conditions. And to date, we have used it for planning purposes, to analyze structure, for preservation and conservation, and even during construction for fabrication of different components. And due to advances in accessibility and cost, we have gone from using it as a novelty tool to having it become a standard service when dealing with existing resources. The evolving project workflow provides many benefits to the design and documentation process. And this is really great for new architecture when you're designing something from nothing. But when working with existing resources, you need a really good base to start from to accurately analyze and test designs. And point clouds have stepped up in a major way to fill that gap for us. They provide the confidence to move forward quickly and accurately into design and planning phase of a project. And beyond providing a crucial and accurate base, point clouds let us gain access to otherwise dangerous or difficult to survey locations, and they let us capture a level of detail that wouldn't be possible or really efficient if we were surveying by hand. Many times our projects are far away from our office, so our time on site is really valuable. And the more we can focus on the intimate details of a project and discuss the overall big picture ideas and spend less time hand measuring things that the point cloud can pick up, the better. And then finally, we use the point cloud itself to non-invasively analyze structure and observe irregularities and patterns that are not always obvious to the naked eye. And this project up here is actually right by the mine shaft that the previous presenter was showing up in Calumet, Michigan. It was part of their mining operations to clear the tracks up in the upper peninsula of Michigan, where on average they used to get like 134 feet of snow per season. So it's pretty wild up there. But we didn't start using a high-definition survey very much until we learned to best take advantage of it and understood the importance and the impact point clouds could have to us in our projects. I have a few projects I'll share quickly that sort of go over some of the diverse capabilities and the benefits of the technology and how we use it as an architectural office, and how our use of it has evolved over time. And also, each of these projects also gave sort of a little bit extra bonus value to the project, something we didn't necessarily ask for from the point cloud, but we found more value in it as we went through the project. So the first example is a 19th century Beaux-Arts structure located in Detroit, Michigan. It's the entrance to a park along the Detroit River. And this was actually our earliest use of point clouds and laser scanning in our office. The project was a design-build restoration effort that involved dismantling portions of the memorial, rebuilding the brick back up beneath it, and then resetting and replacing stones as necessary. When the project was completed, we were tasked with creating a set of detailed, as-built documents, noting all the stone joints and identifying the scope of the restoration work. The only problem was we started documenting in January, which is not a fun time to be outside in Michigan. And if we add to that the extremely detailed and ornate nature of the memorial itself and the lack of access to the upper portions because at this time the scaffolding had been taken down, we decided it might be a good chance to jump in and test out laser scanning and see how it could help us out. I believe initially we budgeted 5 weeks to survey and document the entire project. And that was all based on our traditional methods of going out and hand measuring and photography. But once we got set up using the point cloud, which only took an afternoon to learn, I think we had the entire set done and out the door in under 2 weeks. And we did it at a level of detail and accuracy that would not have been possible had we surveyed by hand. So the entire process sort of took us by surprise, and it was from this experience that we were able to move forward with confidence into other projects and test out different ways to use it. This project was, it's a reflecting pool in Detroit, Michigan. It's part of Minoru Yamasaki's McGregor Center on Wade State University's campus. Years of neglect had left the concrete pool in a deteriorated state, and it was no longer, it was unable to hold water. So our goal is to recapture Yamasaki's original design by repairing the pool structure, restoring the sculptural gardens, and repaving the terrace to allow free and accessible movement around the site. The process would require removing the various components that create the reflecting pool and its landscape, including the monolithic bridges that span from the terrace areas to the islands, the sculptures that sort of littered the landscape, and the various large stones which were within the pool themselves, and then repairing the pool structure and the paving around it and resetting everything back in the same position. We had this project scanned for one reason. The site itself was simple and geometric, but the assorted pieces needed to be reassembled in the precise arrangement as when we started. And the stones in particular were pinned in place with steel supports at some pretty odd angles. We thought they were just resting on the concrete. When we went to investigate, we realized some of them were suspended and tilted up at odd angles the way that Yamasaki wanted for when the pools were filled with water. So we used the point cloud to create our existing condition drawings, but we also made diagrams for reassembling all the different components during construction. And this is one of the projects where we got a little bonus value out of the point cloud. We unfortunately found another use for the cloud on this project. As repairs began on the reflecting pool, the structure started to disintegrate as the contractor was working on the pool walls. And it left basically a steel skeleton of reinforcing where those walls once stood. And you can see in the picture here, the steel was almost in perfect condition and the concrete was just falling away from it. And further investigation and testing revealed that the entire structure needed to be replaced, which our core samples had not led us to believe. So luckily we had the point cloud, which we could use to go back and accurately provide a record of what was there before the contractor started demolition, because he was pretty quick to go around and demolish everything before we could get back out to the site. The next project is the Quapaw Bathhouse Dome in Hot Springs, Arkansas. It's actually in Hot Springs National Park. And the scope of work on this project was to write a conditions assessment report after investigating the dome and its structure. So it was a little different from previous projects in that we were not producing documents from our scan. The dome itself had a long history of repairs and damage, including current issues with water infiltration. We had the dome scanned on this project to provide a base to create diagrams from, but more importantly to try and gain an understanding of the structural shell of the dome itself, with the hope of identifying any patterns or irregularities that might be contributing to the problems we were seeing. And this was our first attempt at using point cloud technology for something other than strictly drawing up existing conditions. And it revealed something previously unknown based on historic core samples and drawings. The dome was up to 1.5 inches narrower across the midsection of the structure, and the deviation in the thickness corresponded to the same place we were seeing cracks at the interior. Ultimately, it was determined that the change in thickness was not enough to have an impact on the structural integrity of the dome. It was just a remnant of the construction methods at the time, but it did help us understand more about the dome, and was a completely non-invasive process, which was one of the goals on this project. And then we also got a little bonus on this project as well. Scanning the dome only took a few hours, and our engineer was down there for 2 days with us. So he spent the rest of his time walking up and down Bathhouse Row, which is pictured on the bottom, and he scanned the exteriors of all the other bathhouses. So now in the future, the park, or we have that as a record of that current condition and configuration, so they can use that for any future projects they have and keep it on archive. And this last project I'll share is the Ottawa Street Power Station. It's in Lansing, Michigan. We worked with multiple people on this project. We were the historic preservation architects, but this was converted into an office building for an insurance company, and they also put a new addition off to the side. Our job was to create the base Revit model, but we did this in Revit prior to having access to point clouds in Revit, so we went through a process of using it in Cloudworks and AutoCAD to create 2D drawings, then converted those 2D drawings into our Revit model, which now is not the case, but it was our first sort of foray into using point clouds and converting that into a three-dimensional model to document construction from. The existing building was a really large open volume, and some of the spaces were up to 9 stories tall, and they were riddled with steel grating and catwalks, so it wasn't a really nice area to walk around in and hand measure. It was too dangerous, and it was really inaccessible by hand. So that fact, combined with our past experience, we decided to go ahead and have the entire building scanned on the interior so we could use it to document the project. And this was our largest project at the time. I think they did almost 200 scans on the interior, which was a lot considering the entire thing was open up. And the benefits I talked about earlier relating to our evolving project workflow and supporting technology can now come into play once we've used the point cloud to create an accurate base model of the building. Once the model was built, we were able to run energy and solar studies on it for the new design, and the team could work with confidence knowing that the base came from solid information. And this project also has some bonus value. The contractor discovered during construction that we had used a point cloud to create the base model. So together with the point cloud and the base model, he did all his steel fabrication straight from the point cloud without doing very much field verification. Then he just designed in some slip joints in the steel to make up for any errors that might be in the model or the point cloud. And that saved him a lot of field time, I know, because he didn't have to rig up people to go through and measure everything. So using the benefits and features granted by laser scanning technology, we are now able to confidently and more quickly document a project. And not only that, but we can more fully understand a project by directing our limited field time to the more intimate details and the overall big picture of a project, rather than spending our time surveying the less important but essential parts. Revit, which we've been using for a long time to document existing buildings, has worked against us until now. Revit requires users working on existing structures to model the entire project before you can even begin documentation. And what used to be stressful guesswork, piecing together disparate fragments of information, is now remedied with laser scanning for us and point clouds. For the architecture and preservation industry, I believe point clouds act as sort of a missing link in the evolution of our current project workflow. And recent mainstream adoption of this technology, for instance, we can now use point clouds directly in Revit, has sort of made this a no-brainer for us as we move forward. And we start to offer it now as a standard service on most of our architectural projects, because we find that a lot of people on the project team take advantage of it and can help sort of share the cost of that and earn some more value out of it.